What exactly is partitioning in the context of databases?
A single machine has limits in terms of storage and the amount of requests it can handle at once.
And you mentioned that partitioning is important for scalability. But how do databases decide how to split up the data and assign it to partitions? Hello, and welcome to another episode of the Trending Tech Show. I'm your host, Alex, and today we're diving into a topic that's fundamental to building scalable systems: partitioning in databases. Joining us is database expert Adam, who's going to help us break down what partitioning is, why it matters, and how it works in practice. Adam, welcome to the show.
Hey Alex, thanks for having me. I'm excited to explore partitioning with you. It's one of those foundational ideas that powers modern data systems, but often flies under the radar.
Awesome. Let's start at the top. What exactly is partitioning in the context of databases, and why do we need it?
Great question. Partitioning, sometimes also called sharding, is the process of breaking up a large database into smaller, more manageable pieces called partitions. Think of your database as a huge library. If you only have a handful of books, you can store them all in one room. But as your library grows to millions of books, you need to spread them across different rooms or even different buildings. Each room, or in our case, each partition, contains a subset of the data. This approach is necessary for scalability. A single machine has limits in terms of storage and the amount of requests it can handle at once. So partitioning lets you distribute both the data and the workload across multiple machines.
That makes sense. It's like dividing a heavy workload among several people, rather than having just one person try to do everything. But with so many terms floating around, shards, regions, tablets, and more, can you clarify the terminology for our listeners?
Absolutely. The terms can get confusing because different database technologies use different names. What we're referring to as a partition might be called a shard in MongoDB or Elasticsearch, a region in HBase, a tablet in Bigtable, a vnode in HBase, and a tablet in Bigtable. But regardless of the name, the underlying idea is the same: breaking up data into chunks, so each piece of data fits into only one partition at a time.
Thanks for clarifying. And you mentioned that partitioning is important for scalability. Can you talk a little more about what that looks like in the real world? Why can't we just replicate our data, as we discussed in a previous episode?
That's an excellent point. Replication, having multiple copies of your data, is great for fault tolerance and increasing availability, but it doesn't solve the core problem of scalability for really large datasets. If every node in your cluster has to store all of the data and handle all queries, you quickly hit bottlenecks. Partitioning addresses this by letting you distribute both storage and processing. For example, if you spread your dataset across 10 nodes, each with its own partition, you can store more data and potentially handle 10 times the number of queries you could on a single node, assuming your partitioning is balanced.
Right, so spreading the load evenly is key. But how do databases decide how to split up the data and assign it to partitions?
That's where partitioning strategies come in. There are a couple of primary approaches: key range partitioning and hash partitioning. Each has its pros and cons, and the choice depends on how your data is accessed.
Let's start with key range partitioning. Can you explain what that is, and maybe give us an analogy?
Sure thing. Key range partitioning is almost exactly like a set of volumes in a traditional encyclopedia. Imagine an encyclopedia where each volume covers entries starting with certain letters. Say, volume 1 is A to B, volume 2 is C to D, and so on. Each volume, or partition, contains all records with keys that fall within its assigned range. For instance, if your database stores sensor data and each key is a timestamp, one partition might contain data from January, another from February, and so forth. This makes range queries super efficient. If you want all records from March, you know exactly where to look.
That sounds neat. But what happens if, say, March contains a lot more sensor data than other months? Wouldn't that create an imbalance?
Exactly. That's called skew, and it's a common challenge with key range partitioning. If the boundaries between your partitions aren't chosen carefully, you can end up with hotspots, where one partition receives significantly more reads or writes than others. To stick with the encyclopedia analogy, imagine if most words started with the letter S, then the S volume would be huge and heavily used, while others gather dust. Modern systems often deal with this by adjusting partition boundaries so that data is distributed more evenly across partitions. But it's still a risk you need to watch out for.
Is there a way to avoid these hotspots entirely?
That's where hash partitioning comes in. Instead of assigning data to partitions based on the plain value of the key, we use a hash function, a mathematical formula that turns the key into a seemingly random number. Each partition is then responsible for a certain range of hash values. This typically ensures a much more even distribution of data, because even if your real-world data is skewed, the hash function spreads it across partitions.
So with hash partitioning, is there a downside?
There is. While hash partitioning is great for spreading out the data and avoiding hotspots, it scrambles the order of your keys. That means it's hard, or even impossible, to efficiently do range queries. Remember the sensor data example? If you want all timestamps from March, those records are now scattered randomly across partitions, so you have to query every partition, even if you only need a subset of the data.
So key range partitioning makes range queries easy, but is prone to skew, while hash partitioning distributes load evenly, but makes range queries much harder. Are there hybrid approaches, or ways to combine the benefits of both?
Great observation. Some systems, like Cassandra, use a hybrid approach by designing their primary keys as compound keys. For example, they might use a user ID timestamp combo, hashing only the user ID to assign partitions, but keeping the timestamp as a part that keeps the data sorted within the partition. That way, you can efficiently retrieve all activity for a given user within a time frame, but spread users' data evenly across partitions.
That makes sense, and it sounds practical for applications like social media, where you might want to see all posts from a user in date order. But if hash partitioning is so good at preventing hotspots, does it solve all problems related to uneven workloads?
It helps a lot, but it can't fix everything. Imagine a celebrity on social media who suddenly goes viral. All their followers are generating a flood of reads and writes related to that one user. Even with a hash, because all those interactions are for the same primary key, the celebrity's user ID, they all end up at the same partition, creating a new hotspot. So the application may need additional techniques, like splitting the key artificially, maybe by adding a random prefix to the key, so that the load is spread across multiple partitions. The downside is that reading the data back now becomes more complex, because you'll have to pull from multiple keys and combine the results.
So ultimately, there's no one-size-fits-all answer. Trade-offs are inevitable.